potential energy problem. Um, the question is a 20-kilogram cart that is to be rolled up a 5-meter long, 2-meter high ramp. How much average force must be exerted to move it to the top of the ramp? So that's the first question. Then, if the cart began to roll back down at the top, what would be the velocity when it reached the bottom? So there's two questions to this one. So let's take a look at it. So here's our little 20-kilogram cart. It's kind of an ugly little cart, I realize that, but so the incline is 2 meters high, and this ramp is 5 meters long. So that's the only information that we're given. So how much average force must be exerted to move this cart to the top? This is just a straight potential energy problem. So the energy is the gravitational potential energy. So that's the only one that's working on it. So we know that the mass of the cart is 20. We know gravity is 9.8 meters per second squared, and we know the height is 2 meters. So this gives us 392 joules. It's asking for, so this is the energy, and it's asking us for the force. So again, this is going to be one of those problems where you have to have a cheat sheet. You have to look at, okay, it's asking me for force. I don't have enough information to solve this with one equation, so it's going to require a couple equations. We know that the work is equal to the energy, and we know that the work is equal to the average force times the distance. So then we just plug this in. So we know that the work is equal to the energy, which is 392 joules, is equal to the average force times the distance. So now we can solve for the force, which is what the question is asking us for. So here again, you're going to have to, have things written out. You're going to have to know by just looking at this what type of a problem is. It's a potential energy problem and a kinetic energy problem, and how do you get the force from that? So it's 78.4 newtons. Now, the second part is how much, once the cart is up here and we let go of it, what is the velocity when it reaches back down here? That is, again, a very simple, straightforward conservation of energy problem. So initially there is no kinetic energy because it's just sitting here. It's sitting right here. It's all potential energy. So by the time it comes back down here, it's kind of like the physics book problem. It has no more potential energy because it's reached the bottom. There is no distance for it to have any potential energy. But it's all kinetics, meaning it's all speed. So we have the potential energy initial, which we solved, right? Here's the energy, and it's all potential, gravitational potential energy. So that was nice. And then the kinetic energy is 1/2 mv squared, and that would be the velocity here at the bottom, which we know 1/2. We know the mass is 20 kilograms of v squared, so that 20 divided by 2 is 10 velocity squared. So v squared is 392 divided by 10, which is 39.2. We have to take the square root of 39.2 to get the velocity at the bottom here, which is 6.26 meters per second. Okay?